Hi guys, so we're going to start Unit 5 today, which is Similarity. So just to kind of give you an idea of what I mean when I say similarity, shapes that are the same are going to be similar figures. So they can be different sizes, but they have to have the same shape. So it's kind of like a less specific version of congruence. Congruence means you got to have same shape and same size. Similarity just means same shape. So we're going to start off with the transformation that will create similar figures, which we hopefully know as dilations. So dilations, remember, either enlarge or shrink figures. So they'll keep the same shape, but the size will be different. So dilations, remember, aren't rigid motions. So let's flip to page 1, and we have some vocab here. So like I said, a dilation is going to create similar figures. So dilations are transformations that produce an image that is the same shape but different size. So creating similar figures. So first thing here, dilations are not rigid motions. So remember, rigid motions are reflections, translations, and rotations. So those are the types of transformations that preserve congruence. Dilations do not, but dilations create similar figures. The notation for dilation, kind of like how we have the notation for rotations, reflections, translations, dilations are going to be a capital D, and then you're going to have some coordinate here. It's either going to be given to you as a coordinate or it might be given to you just as a single letter, meaning a point, depending on if we're doing a dilation in plane space or on a graph. So this coordinate or point is going to be called the center of dilation. And that's basically where every point is being measured from. So it's either all of the points it's where they're being expanded or contracted from. So that's going to be a key point that we look at when we do these dilations. And we'll write the definition down below. So just for right now, that in the notation, that's the center of dilation. And then this K is called the scale factor. And that's basically telling you, okay, you enlarge your original figure by 2. A scale factor of 2 means it's getting twice as big. Or you're reducing it by a scale factor of 1/3, so it's getting 3 times smaller. So that's what number is going to go there. It's going to tell you either to enlarge or to shrink and by how much. A couple other things about dilations. So dilations are going to keep angle measures the same. So keep angle measures. In order to have the same shape, you got to keep angle measures. But they change side lengths. And that's what's going to create them getting bigger or smaller, because the side lengths will change, but the angle measures will stay the same. Now, when we change the side lengths, they're actually still going to be they're going to be proportional to each other, because the scale factor will be the same. And we'll talk more about that later on. But dilations create similar figures, which is why our unit is called similarity. So like I said, similar figures, just to kind of give you an idea right now, but this whole unit we're going to be talking about similar figures, means that they have the same shape, but different size. Meaning same angle measures, but different side lengths. And like I said, there's 2 different types of dilation. So there's an enlargement versus a reduction. So an enlargement means that your scale factor is greater than 1, so that K value will be greater than 1. So for example, 2 would mean it's going to get twice as big, or 3, it's going to get 3 times as big. Where if your scale factor is less than 1, so if K is less than 1, it's going to be reducing. So it'll get half as big or 1/3 times big, something along those lines. If the scale factor equals 1, then basically nothing's occurring. It's not going to get bigger or smaller, so we wouldn't really call it a dilation. It would just be staying the same. So that's why it's either greater than 1 or less than 1. So here's an example right here, these 2 penguins of a dilation. So depending on which one I started with, if I started with the smaller one, I would say that enlargement happened. If I started with the larger one, then I would say reduction happened to get to the smaller one. So that's just kind of to show you. If we're looking at these triangles, here's a way looking at the scale factors. So again, if that scale factor is less than 1, and notice this says that it's greater than 0, we don't think of it as a negative scale factor. So if the scale factor is between 0 and 1, so that's really up here when I say reduction, I'm talking about a fraction or a decimal as the scale factor. So greater than 0 but less than 1. So what's happening, if you look at the original triangle, ABC, it's becoming smaller, A prime, B prime, C prime. What's also important to look at is this point right here. So this is the point where everything's being expanded or contracted from. Remember that this is called the center of dilation, which is always going to be that first coordinate or that first point in the notation. So this is the center of dilation. And what happens when we're doing these dilations, well, this distance here, so if you look at the distance from the center to the original point B, and then after you do the reduction, because this one's going to be a reduction since the scale factor is between 0 and 1, what happens is that distance now from the center to B prime, it looks as if it's half as big. So in this case, the scale factor is probably 1/2, because if you look at the overall triangles, the green to this pink color is about half the size. The A prime, B prime, C prime is about half the size of ABC. So it looks to me as if it's probably a dilation of 1/2. But the important thing here is that distance is shrinking. So from the center to B, that distance is probably double the distance between the center to B prime. Where if you look over here at the enlargement, when K is greater than 1, the scale factor being greater than 1, look at that distance now. So I started with the green triangle this time, and now when I get to this pinkish color, this triangle looks much bigger. It almost looks like maybe it's 3 times bigger. So if you look at, well, here's your center of dilation again. So every point is being measured from the center of dilation. What's happening is if I look from the center to B, well, when you, after the dilation from the center to B prime now, that distance is probably about 3 times as long as this original distance. And that's true for every set of points. So from the center to A, in comparison to the center to A prime, that distance is probably 3 times the length as that original distance. So when we go to do these dilations, everything is based off of that center of dilation. So that center of dilation is so important because that's what you're measuring from. So in order to make a triangle twice as big or half as big, depending on if you're enlarging or reducing, you're always going to start at the center of dilation and you're going to measure that distance to the original, and you're either going to double it, triple it, or maybe make it half as big, something like that. So let's, before we flip to the next page, let's just actually write the definition of the center of dilation down here. So just kind of make a note. So the center of dilation, because we keep talking about it, but let's make sure we have a definition, because that center is going to be that most important piece here. So the center of dilation is going to be the point where all points are expanded or contracted from. And then the scale factor is really going to be that ratio that enlarges or reduces the image. So let's add that as well. So the scale factor is the other important piece. And remember, that's the letter K. That's going to be the ratio that enlarges or reduces the image. And then once you are good with those definitions, let's actually try some dilation. So the first thing we're going to do is we're going to dilate a triangle in plane space, so meaning not on a graph. So you're going to need your compass and straight edge for this because there's no grid to be able to count. And then we're going to look at on a graph. So make sure you guys have your compasses and straight edges handy so we can use those on the next page. So again, dilations in plane space. One other thing to kind of make note of here is that center. So if you look here, that center, in this case, point O is the center of dilation. If we're dilating some point, so like in this case, we're dilating P, and it's an enlargement, notice that P prime is still on that same line or ray that you want to draw through the center and your image and your pre-image and your image. Same thing with this. So if you're doing a reduction, all of these points are collinear. Collinear means they're all on the same line. Where if your center of dilation is the point that you're trying to dilate, it's not going to do anything. It's just going to stay in place. So it's kind of like when you do a reflection, and if the point's on the line of reflection, it stays in place. Same thing with this. So let's actually go and look at our first example. So first thing you want to do is we want to construct the image of this triangle after dilation that's centered at C. So this point is our key point here. This is where everything is going to be measured from. So this is the center of dilation. So when we measure these distances, it's all coming from point C. And we have to have a scale factor of 2, which means the distance from the center is going to get double. So the distance from center is doubled. So when we want to create a triangle that's double the size, that really means we have to double the distance when we go to measure from this center of dilation. And using that property from up top, the center, S and S prime, all have to be collinear, meaning they all have to be on the same line. C, T, and T prime all have to be on the same line, and C, R, and R prime all have to be on the same line. So the first thing I would recommend doing is actually drawing, I would just do like a dotted ray off of C passing through S. So let's go ahead and do that. So just make it dotted real light, because we know that S prime is going to have to be somewhere on this line. And then I'm going to do the same thing through all of the other points here. So let's go ahead and do that. So we're going to go from C through T and extend it out. Remember, you're doing this very lightly. And then we're going to do the same thing from C through R. Lightly dotted, because we know that S prime, T prime, and R prime all have to be on these dotted lines. So then once we have those, then we're going to take our compass and we're going to measure. So let's say we want to copy R prime first. We want to find R prime. What we're going to do is we're going to copy this distance. So we're almost like copying a segment here. So I'm going to take the compass and I'm adjusting it so that the point is on the center of dilation, because remember, everything is about that center of dilation. It's all getting measured from that. And I'm adjusting my compass so that this opening is on point R. And I'm going to mark it just to represent that I did measure it. And since we're doing a dilation of 2, we need to double the distance. So R prime needs to be twice as far away from C as R was. So this is 1 length. I need to double it. So that just means I need to do 1 more of them. So then I take my compass, I move it to where the arc is, and I have now doubled that distance. So C to R, R prime, it's going to be right here. This is double the distance away from C as R was, because I copied the length twice. Then we repeat the process. So if you didn't see that one, watch the next one here. So I'm going to go from C, everything's from that center. Now I'm going to measure to T. So again, I'm just going to put an arc there to represent I've measured it, and then I also need that arc so that I know where to place the pointed part of the compass. So that's 1 length from the center to T. I'm trying to double that because it's a dilation of 2. So now I take and I put the pointed edge on that arc, mark it, place your point, call it T prime. Last point here is going to be for S. So now you're going to mark an arc and then repeat it. And if for some reason your lines, your dotted lines aren't long enough, to just extend them, because you have to see where the arc intersects with the dotted line, because remember, all the points have to be collinear. They all have to be on that same line. And then once you have this, now you can see if I connect these 3 points, so using my straight edge, connect the 3 points, you have a triangle now that's the same shape as the original, but it's doubled in size. The lengths are all double. So there's your dilation. The instructions are down below too, so if you need them, they're down there. So now you can set your straight edge and compass aside, and we're going to move on to doing these in the coordinate plane, which I think are almost easier because you can just count. So we'll go to the next page. And when we get to this page, we're going to go ahead and plot our triangle to start with. So we're starting with triangle ABC. We want to draw the dilation image of the triangle with a center at the origin. So that's going to be an important point here. And a scale factor of 2. So we're going to essentially do the same thing that we just did, but instead of having to use our compass to measure, we're going to use the graph. So let's go ahead and start with our original triangle. So we have 0, 2, 2, negative 1, negative 2, negative 2, and I'm going to mark that center because that's an important thing here. The center is at the origin, which means 0, 0. So we're going to start at the origin. So this is going to be our center, that red point. And we're going to measure the distance from the center to each point, each pre-image, to get the dilated figure. So I'm going to measure from the center to A is 2 units. So if I'm doing a scale factor of 2, that means you need to double the distances from the center. So I count from the center to A is 1, 2, double it. So instead of going up 2, go up 4. 1, 2, 3, 4. So that's where A prime goes. So I'm going to go ahead and state that. So A prime is going to be 0, 4. Then to get to B, you can't count diagonally, so you're going to just have to count over and down, kind of like when you do slope for the midpoint. So it's going to be over 1, 2, down 1. So we're going to double that. So instead of going over 2, down 1, you're going to go over 4, down 2. You're doubling the distance to get to B. So 1, 2, 3, 4, down 2. 1, 2. That'll be B prime. And then to get to C, I had to go 1, 2, down 2. So I went 2 to the left, down 2. Just means I'm going to double it. So I'm going to go 4 to the left, down 4. So 1, 2, 3, 4, down 1, 2, 3, 4. And that'll be C prime. So it's that same concept, it's just counting versus using a compass. So then let's just make sure we state our coordinates. So B was 1, 2, 3, 4, so 4, negative 2. C prime was negative 4, negative 4. And that's it. So now some of you might notice a pattern here if you look at ABC in comparison to A prime, B prime, C prime. If you look at just the coordinates, you should see a pattern. And the pattern that you should see is that really we just multiplied all the coordinates by 2. So 0, 2, I multiplied by 2 to get 0, 4. Then I took and I multiplied each of these by 2. Then I took and multiplied each of those by 2. Now this only works because it was centered at the origin. So you were starting at 0, 0. So essentially when you double the distances, you're really just multiplying the coordinates by whatever that scale factor is. It will not work if it's not centered at the origin. So for this page, all of our dilations are centered at the origin. The other page, they're not, so it won't be the same process. So you can just multiply by 2 because dilation was centered at the origin. Was centered at the origin. And it's because your coordinates are really like your distances when it's centered at the origin. So let's look at the next one here, example 2. So for this one, you're centered at the origin again, scale factor of 1/2. So really you could take and divide each of these coordinates by 2. Multiplying by 1/2 is just like dividing by 2. But I want to show you graphing because for the next page you have to know how to be able to do this graphing without counting on that rule. So I'm going to start off the same way, plot my points. So -2, 1, 2, 3, 4, 4, 4, 2, -2, -4, -2. 1, 2. And again, make it known which point's the center. So in this case, I'm just going to mark it with the red dot. So there's my center of dilation because it was at the origin, 0, 0. And the scale factor of 1/2 means that the distances from the center are half as much. So basically we're going to divide by 2. So divide by 2 for the distances. So what I'm going to do is I'm going to count from the center to A was left 2. So I went left 2 and then up 1, 2, 3, 4. So half of that would be left 1 up 2. So left 1 up 2. That'll be A prime. Then to get to B, I had to go 1, 2, 3, 4. So right 4, up 1, 2, 3, 4. So half of that would be right 2, up 2. 1, 2, up 2. And you see that your figure is getting smaller, so that's good. So then to get to C, I went right 2, down 2. So right 2, down 2 means you're going to go right 1, down 1. Right 1, down 1. And then to get to D, I had to go 1, 2, 3, 4 to the left, down 2. So 2 to the left, down 1. There's D prime. And there's your figure. So we have A prime, B prime, C prime, D prime. Essentially what I did, if you look at these distances are really the coordinates. So when you go right 4, up 4, it's positive 4, positive 4. If I go left 2, up 4 as a coordinate, that's -2, 4. So see how those distances, when it's centered at the origin, are really the coordinates? So that's why when we're dividing the distances by 2, we're really coming up with the new coordinates. So the new coordinate for A prime is left 1 up 2, really means -1, 2 on a graph. So that's the reason why this is working. So -1, 2 was prime is going to be 2, 2. C prime will be 1, -1, and D prime is going to be -2, -1. So if you look, again, the rule, really what I did here was I just divided everything by 2. The x and the y values both got divided by 2 for all of them. So remember, this only works because it was centered at the origin. If you look, here's the rule down here again. So if it's centered at 0, 0, the origin, then the rule for dilations is that you multiply each x and y value by whatever that scale factor is. And it's really because when it's centered at the origin, those distances are those coordinates. So let's look at ones that are not centered at the origin. So on the next page, we're going to start off the same way. Let's start by graphing our original picture. So we have -3, 6. So that's going to be A. We have 3, 6. We have 3, -2. And -3, -2. And if we read what we're trying to do here, we want to draw the dilation with the center at point A and the scale factor of 1/2. So what this is saying is we're going to look at point A, and that's going to be our new center, and that's what we're going to measure those distances from. So the distances we're going to basically divide by 2. So the distances from the center we divide by 2. So find the distances from the center and then divide by 2. So if I'm trying to do a scale factor of 1/2, it should be getting smaller, the rectangle. So to get A prime, since the center is A, I don't move anything from A, so it's gonna, A prime is gonna stay right here at the center, so that won't change. So the coordinates of A prime are gonna be -3, 6. That's the exception. Whenever your center of dilation is one of the points, it'll just stay there. That was one of the rules from a couple pages back. Then to get to B, I had to go 1, 2, 3, 4, 5, 6. So I had to go right 6. So instead of doing right 6, I'm going to go right 3, half of that. 1, 2, 3. So there's B prime. So that's the coordinate 0, 6. Then to get to C, I had to go right 6 and then down 1, 2, 3, 4, 5, 6, 7, 8. So right 6 down 8 means I'm going to do half of that, right 3 down 4. So right 3 down 1, 2, 3, 4. We'll get to C prime. So C prime's coordinate is going to be 0, 2. And then the last one, D, I had to go down 8. So that means I'm just going to go down 4. So 1, 2, 3, 4, D prime ends up here. Connect those points, and we get our new dilated figure, which is half as big as the original. So D prime is the last coordinate I want to state, which is going to be -3, 2. So let's try another one like this. So instead of, in example 2, instead of it being worded like a description, it's going to give us a dilation in the notation format. So remember, when you see this, that first coordinate is the center of dilation. And this 2 represents the scale factor. So that means you're going to double the distances from the center. And this center is not one of our coordinates, so it's just going to be a point that we're going to use to measure those distances. So let's go ahead and try that. So let's first graph our original. 1, 2, 3, 4, 5. So here's D, 5, 5, 2 down 1, E, and F is 6, -3. So 2, 4, 6, 1, 2, 3. So here's the original. And if my scale factor is 2, the new triangle should be twice as big. The center, remember, is an important point here, is going to be 8, 3. So 2, 4, 6, 8, 1, 2, 3. So here's the center. So this is what I'm measuring everything from. So to get to D, I had to go up 2 and then right 1, 2, 3. So I went up 2, right 3, right 3, left 3. So up 2, left 3. So you're going to either repeat that process to double it. So up 2, right 3 again will get you D prime, or double it. So if you repeat it, you're essentially doubling that distance. It's more like what we do with the construction, where we use the compass and double it. It's going to be up 4, right 6. So if you look, I went up 1, 2, 3, 4, left 1, 2, 3, 4, 5, 6, left 6. I keep saying right instead of left. And then from the center to get to F, we had to go left 1, 2, then down 1, 2, 3, 4, 5, 6. So you could repeat that. 1, 2, down 6, 1, 2, 3, 4, 5, 6. So again, doubling the distance, or you can just say, okay, went down 6, left 2, which tells me I'm doubling that. Down 12, left 4. And then the last one, same thing, count to get to E. So 1, 2, 3, 4, 5, 6. Down 1, 2, 3, 4. So left 6, down 4. So then you repeat it. 1, 2, 3, 4, 5, 6. Down 4. 1, 2, 3, 4. Again, that distance should have been left 12, down 8, or you just double it when you're counting. Whatever you think's easier. You don't have to record these distances as you're doing them. It's just so that you're keeping track of it, so you don't forget. So you either repeat the distance or keep track of it, depending on what you think's easier. And then I connect my points here. I get my new triangle, which should look double the size as the last one. And it does, so that's good. So then we need to just state our coordinates here. So we have D prime is going to be 2, comma 1, 2, 3, 4, 5, 6, 7. So 2, comma 7. E is going to be 1, 2, 3, 4. So negative 4, down 1, 2, 3, 4, 5. And then F prime, 1, 2, 3, 4, down 1, 2, 3, 4, 5, 6, 7, 8, 9, so negative 9. So there are your coordinates. So when you compare examples 1 and 2, you should see that there's no pattern from these coordinates to the primes. So there's no specific like rule that you're multiplying by. You definitely didn't divide by 2 or multiply by 1/2 in this case, because it's not centered at the origin. Again, if you compare these coordinates, you can see that I didn't multiply by 2 to get from 5, 5 to 2, comma 7. So the rule doesn't work if it's not centered at the origin. So just remember that. And then the very last thing we're going to look at is on the next page. And that's going to be, now they're giving you this information and they want you to find, after this dilation, they want you to find the center of dilation and find the scale factor. So in order to find the center of dilation, if you remember that property from a few pages back that says that the pre-image, image, and the center of dilation are all collinear. So if you can't see, like sometimes you can kind of just eyeball it and see where it is, but what you can do is you can connect each pre-image and image point. So if I draw a line through B and B prime, and then I draw a line through C and C prime, and if I draw a line that connects from A to A prime, you can see that where these are all crossing is at the center of dilation, because all of those points have to be collinear. And this is a little bit off. So it looks like if I actually fix this, my center of dilation is going to be at the origin. So some of you might just be able to eyeball that and see it right away, which is fine, but this is how you can definitely check it, because the center, pre-image, and image are always collinear. So for this, the center of dilation is going to be 0, 0. And then to determine the scale factor, really what you want to do is you just want to count from the center. So how did we move from the center to the original, and then how that changed when we moved to the primes. So in this case, I can definitely tell that this was an enlargement, because if I compare the pink triangle to the green triangle, it got bigger. So if we look, if we measure to get from B to B prime, let me get rid of these lines, just delete this line here. So if I'm looking at from the center to B, left 1 up 2, to get to B prime, I had to go left 2 up 4. So I went left 1 up 2 first, and then the second distance was left 2 up 4. So essentially what we did was we doubled it. We multiplied those distances by 2. So that tells me my scale factor equals 2. And then for the last one here, if you're looking at the center of dilation, well, if you see any spots where the points are the same, so the pre-image and the image points are the same, so in this case right here, E and E prime are the same coordinates, that has to be the center. I mean, you can check it where if you draw lines through G, G prime, H, H prime, F, F prime, they're all going to intersect at that point. So that's another way to determine the center. But really, whenever you have an image and a pre-image that's the same point, that has to be the center. So the center is going to be -2, -2. And then if you're looking at the original, which is the purple rectangle to the blue, it was a reduction. So we know a reduction occurred, so that tells me that my scale factor has to be a fraction. So if I look at from the center to, let's say, F, well, the original distance was 1, 2, 3, 4, 5, 6. The new distance was 1, 2, 3. So to go from 6 to 3, we had to divide by 2. So that tells me my scale factor equals 1/2 if you're dividing by 2. So that's it for that. There is a formula that we'll talk about at some point, how you can come up with the scale factor when it's more difficult to find. But for these, it's pretty easy just to be able to count it. So that's it for today.